Gosh, thank you so much for that introduction. I hope I am not just a passing comment talking of phenomena. So first of all, I want to say what a privilege it has been to be at KITP, and I would like to thank Lars for ably running these absolutely fantastic programs. They are very, very exciting because of the pools of people that can actually come here to Santa Barbara, to this beautiful place, and discuss science in a setting where we are unfettered from our usual responsibilities. So, and this particular program, I do want to thank the organizers. It's been fabulous. We just had the conference, and I'm here for a couple more weeks. And I'm afraid, unfortunately, I have to go back and start teaching. But I wish that were not so, but now one could be here longer. Okay, what I want to talk to you about today is our growing understanding of black holes and the role that they play in the real universe. And the reason I say the real universe is that, as Lars mentioned, you might have, and probably a subset of you attended Polchinski's lecture on this new and interesting theoretical debate about information and black holes. So today what I'm going to be talking about is not about information extraction from black holes or not, but the information that we do extract and infer the properties of the black hole, of real astrophysical black holes, that exert their gravitational influence on the environment. And so I just want to, what I want to do in the talk today is to actually sort of lead you through a little bit of the basic technical sets of tools that we now have at our hand to understand black holes and the roles that they play. They play, it turns out, a very, very active role in the universe. They modulate structure formation, which is the formation of all galaxies over cosmic time. And obviously they play important roles at different junctures in the universe over the entire cosmic history. And so the puzzles that have to do with black holes have to do with when they form, how they grow, if they grow, and we now have evidence that there are some very, very massive black holes in the universe, right around our galactic neighborhood even. And so without further ado, what I want to do is to kind of highlight the enormous progress that's happened even since my PhD about 10, 11 years ago. There's been a tremendous sea change in our understanding. And as I said, we've used a different sets of tools. So there's observational data in multi-wavelength data. So it's X-rays, gamma rays, optical data, infrared data. And technology has advanced so rapidly that pretty much the entire part of the electromagnetic spectrum has opened these new windows. Yet, there's one very interesting unopened window that I will talk about at the end, and we are inching closer and closer to opening that window, which is absolutely marvelous. And I really hope that happens in my lifetime. So what we now have is a very well understood theory for structure formation of how galaxies assemble. And we think that dark matter is actually in the driving seat of this process. And basically, dark matter is the scaffolding on which galaxies, stars form, they make galaxies, and they grow. But it turns out integral to this entire structure formation game is the role of black holes. And partly, it appears so, and we sort of started putting the pieces together, because in the nearby universe, we definitely see that pretty much every galaxy around us seems to harbor a central black hole in its center. So first, before I sort of build this story of how we understand astrophysical black holes, I'd like to connect back to why these objects are so enigmatic, right? I mean, they are so enigmatic because of the effect, their extreme gravity and the effect that they have on space-time. So this is just a little artist's cartoon showing the kind of curvature, the extreme puncture that black holes actually engender in space-time. And obviously, you can see that even the sun creates a little bump in space-time, a white dwarf, it's a very compact star, neutron star. They all create bumps. But the puncture in space-time that is created by black holes is very, very special. And however, the astrophysical effects of the black hole are going to be the extreme gravity of this object and what it does to the dynamics of gas and stars that are moving around it in the centers of galaxies. As I said, the centers of galaxies are extremely dense. They are packed with gas, typically, and with a lot of stars. So the way we infer the properties of the black hole, and the key properties we infer are its mass and perhaps its spin, whether it's spinning or not. I'll come to that towards the end. So those properties are really inferred by looking at the motions of stars. Or in the case of the earlier universe, we'll see it will be from the motion of gas that is being sucked in by the gravity of the black hole, and a portion of the rest mass energy of the gas gets radiated out. Typically, it's in the X-rays, but you also see it in the optical. Okay? So let me just give a few basics and a few basic definitions and quantities that will make it very, very easy to understand how we conceive of black holes in the universe. Okay, so instead of a puncture in space-time, right, the way I promise there are not too many view graphs that are laden with equations, but there are a few basic concepts, and if you get them, you're set. So the way I like to think about black holes, and I think is intuitive for the kind of work that happens in astrophysics, is rather than the puncture in space-time, which is kind of exotic and lovely, but it doesn't help us calculate all that much. What really helps us calculate is to think of the notion of escape speed. So essentially, when you have a gravitating object, there is a velocity, a speed that you have to attain to exit its gravitational field, right? And that will, of course, depend on the mass of the body. So if you look at the escape speed, it is typically given by G, this is Newton's constant, the mass of the body divided by the radius, right? And this escape velocity tells you the amount of energy that you have to expend to get, say, a satellite, a rocket, something completely out of the gravitational influence of this body of mass m, right? So now, if the velocity that you give, for example, for rockets that go up from Cape Canaveral, their velocity, the reason we have the boosters is so that you can actually boost them above the escape velocity of the Earth so that they can exit Earth's gravity, right? And basically, then you exit, and then you can choose how much energy you want to give the rocket so that it gets on the kind of orbit that you want it to. So if it's going to the space station, you launch it on a different orbit. So now think of the same concept. And now this is the slightly counterintuitive part. So now if the escape velocity, instead of being some finite velocity that you could sort of burn some fuel, rocket fuel, and send it up, was actually the speed of light. That's the ultimate speed in the universe, right? That's sort of the limiting speed. Now, if that was the escape velocity, now that's a black hole. To launch something off, away from the grip of the gravity of the black hole, it has to be launched at the speed of light, i.e., it ain't happening. So you can't do it. And that's why, you have this radius, which I showed briefly in the sketch. This is the event horizon. So it is at this point, at the event horizon, this sort of size scale of a black hole, this region around a black hole, where the escape velocity is the speed of light. So basically, that is the reason why it's called a black hole. Not even light can escape it. Okay, and that radius is called the Schwarzschild radius. And that is essentially the same formula. Now the escape speed is actually the speed of light. Now for the Earth, if the Earth were to become as dense and have the kind of gravity a black hole would, it would have to be squeezed to the size of less than a centimeter. Okay, that's how dense the matter is packed in. Right? And the sun would have a radius of about 3 kilometers if it were to have the kind of gravity that a black hole would, right? Of the sun's mass. So we're squeezing that mass into this tiny, tiny volume. Okay, so I promise there's this slide, and then there's one more slide, and then we're done. So please feel free to interrupt. Okay, no, the reason they're marked in blue and in black is that once you have a couple of these concepts, you can understand exactly what we're doing today, and you can understand what the challenges are. So the first sort of, you already know what the Schwarzschild radius is. That's the radius, the event horizon, from which not even light can escape. So notice it's proportional to the mass of the black hole. And then there's a region of influence. Basically, it is outside the Schwarzschild radius. It's a region on the scale of which you can imagine the black hole does exert some influence, where its gravity is dominant. So you can get captured and trapped in that region. Unlike the Schwarzschild radius, where once you cross it, you're gone. Basically, you'll be spaghettified. You'll be pulled. This, as you know, is the controversy, right? Do you get fried or do you get spaghettified, right? So I'm not going to go there to the firewall paradox. So the region of influence is this other sort of outer region where you can sort of be trapped by the gravity of the black hole. It's not the point of no escape. You could escape. Depending on the orbit that you have, you could, but it's the region where the black hole's gravity is dominant. So for example, we'll just see in a minute for a galaxy what that size scale is. Just a minute. So the other things, when we want to understand how black holes grow in the universe, you want to understand how do they actually grow. So it turns out that the final mass of a black hole is proportional to its initial mass, and then it sort of is feeding on some time scale, okay? And it grows exponentially. So the mass doubling time, so that naturally gives you sort of the only number, really, the fundamental number in the game is the mass doubling time scale for a black hole. How quickly it doubles it e-folds its mass, right? Now, as you may say,
that's for all black holes?
Yes, for all black holes. And the reason why this is the only time scale in the problem is that anything that happens around black holes, you want to compare to see if it's feasible, whether if it happens on this time scale or faster, or whether it happens within the age of the universe. If a process takes 3 times the age of the universe, it's not feasible. It's not going to happen, right? It's going to take the entire age of the universe for that process to actually happen. So it turns out that the age of the universe, the time elapsed from the Big Bang, really. Because we are trying to form black holes very early in the universe. So the question is, how much time do you have after the Big Bang? And we see some very, very bright objects, these quasars that are growing, feeding black holes, that are supermassive, that are 1 million times the mass of the sun already, when the universe was few 100 million years old. The universe today is 13.8 billion years old. So very soon after the Big Bang, you're actually seeing some very, very massive black holes that have grown, and they're sitting there, and they are shining, so we know they're there. We have evidence, incontrovertible evidence that they're there. So the question is, how do they start their lives, right? How do you grow up? Because now you see how to grow the hole, but one of the key problems is, what is the initial hole? Where did the first black hole come from, right? And how big was it? So the other thing we need to do when we want to understand the feeding habits, the feeding is obviously how you're growing, and is this quantity called the accretion rate, like how quickly you eat mass, basically. And all mass here is gas. It's typically hydrogen. Most of the universe, as you all know, is basically hydrogen, right? So what you're really accreting is gas, hydrogen gas. And the accretion luminosity, as I said earlier, some small portion of the rest mass energy, E equals mc squared, is the total energy of any mass m. Some small portion of it gets converted into radiation. And you see that. That's how you know there's a black hole there. Yeah? No, actually, the density of dark matter is an excellent question. It's a problem that I got very excited about as well when I was in grad school and calculated it. It turns out the density of dark matter overall, the mean density is too low for that gobbling rate to be important or interesting. So in principle, yes, you could have, but the flux, the amount of dark matter that you would have in a supermassive black hole today is teeny weeny. It's really very, very minuscule. And it's mostly baryons, gas, that gets accreted. Of course, the black hole doesn't care what it eats, and we wouldn't know. When we see a black hole, when we infer the presence of 1 million solar mass black hole, like the one in the center of our galaxy, we have no idea what portion of it could have been ordinary atoms, hydrogen, what could have been my unmatched socks, what could have been dark matter. You actually have no idea what actually went in. That's an excellent question. And you have this interesting sort of cap in the luminosity, the total amount of luminosity that you can get from accretion. And that's a simple limit that helps you figure out when the black hole, the luminosity from the energy output from the black hole, it's a cap that tells you when you will actually destroy your gas reservoir, because you need a gas reservoir to feed. And that limit sort of gives you, because it balances gravity to the accretion luminosity, the radiation pressure that the gas has, in a way, it sort of tells you, it gives you a limit, the maximal rate at which you can accrete, in a rough way.
So the same thing works inside stars.
Yes. Radiation pressure, yes. Radiation pressure plays an important role. Yes, and basically the equations for stellar structure come from balancing radiation pressure of hydrostatic equilibrium, yes. Okay, so what is the challenge in studying astrophysical black holes? The challenge is really one of physical scales in the universe, right? So as I said, these 1 million solar mass black hole, the Schwarzschild radius at that point of no return, the surface where the escape velocity is c, is the size of, say, a penny, right? And what you find is that the entire problem that you need to solve for the gas that is going to flow in, that's going to get accreted, etc., the gas has to come from does come from very, very large scales. It comes all the way out from very cosmological scales, where structure forms and gas flows in. And so if you look at the range of scales, so the stellar extent, so the black hole is sitting at the center of a galaxy, and the galactic nucleus, as it were, the inner region, the sort of the stars that are in the innermost region of the galaxy, 10 to the 20. So notice the scale here, you've gone up by 8 orders of magnitude. The stellar extent of the galaxy, the stellar distribution of a galaxy can be quite extended. So that's that. And then you have the dark matter halo of a galaxy. Now we know that most galaxies, if not all, possess extended dark matter halos that are sitting well outside where you see the light, right? And then you have cosmological scales. So the challenge of the black hole feeding problem is that the gas has to go from this scale all the way down to the center. That's a challenge. That's a huge challenge. And what I'll try and show you a little bit, yeah? No, if that was the size of a penny, then this would be the size of the Earth. That's why they're in black. That's not the size of a penny. Penny is about 8 centimeters. So this is like my trying to do a clever scaling argument. Say that if that was the size. Yeah. So you can imagine that one needs to understand physics on many different scales and physical processes that might be important. So for example, the dark matter, looking at the dark matter, right? So dark matter particles are these exotic particles that are collisionless. They only have gravity. We don't know what the particle is, but we know exquisitely how it's distributed in the universe. And so you have the gravitational dynamics of the dark matter, the gravity of the dark matter, the potential well. And you have gas, you have stars. So it's a pretty messy problem. And so what people have done is break it down into various stages, simplify the problem, come up with heuristic models first, and then see if you could do large computer simulations of the physics processes that are not so pared down, where you can add in more physics and then see if you approach what we think are sensible solutions. So what is a sensible solution? A sensible solution is one in which we can build with sort of this framework, how you grow each and every black hole in the universe, how you can build the entire storyline for all the black holes that we see in the universe. So you have now data from various cosmic epochs that you need to knit together, and basically you need to build a storyline that makes sense. A storyline that has physical principles that make sense, that operate at different times and in different environments. So I thought one of you may ask me, and this is something I'm going to come back to at the very end, black holes actually do spin. Okay, so they have spin, they have angular momentum, they spin. And as far as we're concerned, the only thing to note in this artist's rendition is that for a non-spinning black hole, the Schwarzschild radius is larger, it's further out. So the center is really where we think the black hole is. So notice that the Schwarzschild, the point of no return is marked by this dark edge, right? And that's closer in for a spinning guy. So you sample the extreme gravitational field of the black hole closer in for a spinning black hole with the Schwarzschild radius. Okay, so how do you feed black holes? As I said, there's this accretion. This is gobbling of gas. And sort of the gas flows in towards the black holes, produces radiation, and the gravitational potential energy of this gas packet is released. Some portion of it is released. So this epsilon is typically less than 1. So only a small portion is released. It's typically 10% maybe. And so for the kinds of configurations from which we think gas gets fed on finally to the point of no return, basically that's when you add mass, we think that the efficiency, this epsilon, sorry, this should be epsilon, it's E now, is about 10%, okay? So let me just remind you, right? So this is it. So our entire sort of workshop this week has focused on basically these three processes. How do black holes form? So they must form, it turns out, from coagulating gas and aggregating it to very, very high densities somehow to make the little seeds, the starting points, before we can start growing them. And then we need to figure out how to feed them, like how do they actually get fed, and how the fueling, how the feeding is different during feast times and famines, right? So what's the difference? Or does the black hole feed always? Is it always a feast? Or are there periods of famine? And if there are periods of famine, what are the signatures? How do we know when a black hole is feeding? Well, when it's overfeeding, we know it's going to be obese. Now, I'm not joking. This is a new class of galaxies, obese black hole galaxies. And they have really over-massive black holes in their centers. But there are periods when there is either no gas around or somehow the gas has been expelled and it's famine, right? So we'll see what the data is saying about those stages. And then there's this very, very difficult, complicated one because it involves this very large coupling of scales that we just talked about, which is the feedback. Because there's so much energy that's coming out of the black hole that it is obviously going to transform its environment. It's going to heat everything, right? The question is, what does it do? How much does it heat? How far away does it affect things? So these are sort of really the three hot areas of research in astrophysical black holes. Formation, how they form, the first seeds form, fueling, and feedback. So I'll just give you a feel for how we understand each of those stages. So this is just a graphic, a slice from a simulation. This is not a movie. And what this is showing you, so basically the black hole is sitting somewhere here in the center. And what you have here, what you are seeing here is a feeding disk for the black hole. It's a gas disk. This is the amount of gas color-coded by temperature. So the blue is colder and this is hotter here in the center. So this is basically a disk and I've cut it on the side. And so this is how you feed the black. We think our simulations suggest that these kinds of gas flows are what you need right down at those inner regions to get the gas onto the black hole. Okay? But you may ask, where is the most compelling evidence for the existence of a black hole? You're saying, oh, great, sounds pretty vague so far. So what you are seeing here is the motions of stars at the center of our galaxy. Okay? So the center of our galaxy is about 26,000 light years away. For those of you who think in light years, I don't. I think in 10 to the 24 centimeters away. So those are the units that I think in. So, and so there is a black hole in the center, as I said. It appears now the center of every galaxy. And it feels, now that we have these models, it appears for sure that the formation and the growth of black hole has to be intrinsically tied to the formation of the stars and the assembly of the galaxy. It's all part of the same process. So what you're seeing here are the orbits of the stars that are right around the black hole. And remember I told you that in astrophysics, we're going to study the effect of the black hole on the motions of stars or gas or whatever's right around the center. And what you're seeing here are the orbits. Notice the beautiful Keplerian orbits. And one of them has actually closed, right? So this star S2 has an orbit of about 15 years. And it's only 17 light hours away from the black hole. The black hole position of the black hole is marked with this star. Remember, this is projected. You may say, these things are all crossing in. Well, this is a projection. Remember, it's 3D. So what you're seeing here, from the fact that this ellipse has closed, you can actually estimate the mass of the black hole at the center of the Milky Way. And it's estimated to be a few million times the mass of the sun. Okay? And the orbital period for the star is about 17 years. So what you saw here was actually real years. So that we now have enough data to see. So this is a montage of data taken as they were tracking these stars. So this work was done by Andra Ghez and her collaborators at UCLA. So, there's incontrovertible evidence that definitely we have a black hole in the center of our galaxy and for many other nearby galaxies. I'll just show you. So, okay, where do you expect to find the black hole? So typically, we expect it to sink right to the center of a galaxy. So I can't resist showing you this beautiful animation that NASA did for a press conference that we did a couple of years ago. So this is a real galaxy. It's a Hubble Space Telescope image of the galaxy. And to give you a sense of the scales, right, I've just been the penny and the size of the Earth, etc., we're going to zoom right in, and we're going to move in. We never quite see the black hole or the accretion disk, but then we're going to patch on to the artist's impression of how it's all supposed to fit together, right? The zooming in of scales. So every sort of snapshot that you see is a 10-fold zoom in. So what you're now seeing is the artist's impression of the accretion disk, the gas disk, the feeding disk to the black hole. And now we are moving through the disk, and there it is. There's the monster, and remember, where we saw the simulation, we saw a cutout of this, right? So that's really that's what we're all trying to make sense of, how the gas actually reaches this radius. Okay, so what all else do we know? As I said, are galaxy compelling evidence? Are there other black holes? So it turns out that these are all, what you see here in ellipses is data with error bars being the size of this, so it tells you the error. So what is plotted against what? This is the mass of the black hole in the center of a galaxy. These are all individual nearby galaxies. This is a local neighborhood. These are all nearby galaxies, and they all harbor a black hole. Okay? And their estimates, some more reliable than others. As you can see, the error bars, some of them are more elongated, tells you there's more errors. But they all seem to harbor a black hole, and not only do they just harbor a black hole whose mass we have estimated, but it is sort of correlated. This line tells you that the speed of the stars in the nucleus of the galaxy, right? So that is the sigma. And it's measured in kilometers per second, and what you find is the faster the speed of the galaxy, of the stars in the inner portion of the galaxy, which corresponds to a more massive galaxy. So as you go this way, you get to bigger and bigger galaxies, brighter and bigger galaxies. The black hole gets bigger and bigger. So what this tells you is that there has to be some kind of cooperation, if you will, between the stars that form in the inner regions of the galaxy and the black hole that's sitting in the center. No, the correlation is not so strong with all the stars in the galaxy. People have tried that. But this is not surprising, right? Because it's only an influence radius. It seems, to me, this seems quite natural and very plausible and acceptable, right? First of all, you make stars from gas. And from the same gas reservoir, you've got to feed the black hole. So it's not surprising that they have something to do with each other. Second of all, the fact that it's only the stars in the inner part is not surprising, because you know that the region of influence of the black hole, enormous as it is still quite small. It's the inner part of the galaxy. The black hole by itself does not exert its gravity at the far outer reaches of the galaxy. Remember, it's a very large scale. It's very dominant where it is, but its influence doesn't extend far out enough. Yep.
Is there a correlation as to the age of the galaxy and where it lies on that scale?
Not quite, but there is a correlation. So most of these galaxies have populations of red stars, which are old stars. So most of these galaxies are also galaxies where the black hole is not feeding and stars are not forming. New stars are not forming. So they all tend to be galaxies that have older populations of stars. So these are galaxies which are not active in any sense of the word. So basically they have stars formed a long time ago, and they've just been aging. Okay? Yep.
Do the galaxies organize themselves around the black hole?
That is the question. It's one of the questions. I'll come to that. Exactly. So that is one of the key questions that links the formation to the effect that the black holes have. Yep.
You expect the black holes sink to the center, but that means it has to give up energy to get to the center. How does that happen?
I'll show you. I'll show you some simulations that will help you understand how that happens. We actually think they also form in the galactic nucleus because the gas is densest. You're all asking these great questions that are going to make me show off what I've worked on. So I'll come there. I'll get there. Yeah. Yeah.
Progress then on which came first, the black hole or the galaxy?
So I would say it's still unsettled, and I definitely fall in the camp, but I go back and forth on it. But of late, I would think the black holes likely came first. But, yeah, Greg?
I'd like to ask a question. This is a log plot. The slope looks, if I eyeball it, to be about 4.
Yeah, it's 4, 5, 3, 4, 5, given the errors.
Can you understand why it's 4? Because if I look back at your earlier equations, it looked like mass kind of went like the square of the typical velocity. How did it get so large to be 4/5 now?
No, but this, this, remember, these are individual galaxies, right? So each point here is a galaxy. And the galaxy is a full gravitating system on its own.
Okay.
So that V was that was a different. So what you are seeing, so do we understand how this correlation? I think there are many, many possibilities. It seems like, as I said, it's kind of natural. You kind of get this kind of correlation. So actually the question is not so much why we have this correlation, but why do we have the scatter? What causes the scatter? So that's what we're all squabbling about right now. Is there more scatter here? Is there more scatter there? And is there more scatter here? Because actually it's harder to measure here. These are wimpier black holes. And they exert less influence. Their region of influence is smaller. So, it's harder to kind of pin these guys down. So the question really is not so much, and I'll try to give you a feel for how we get that and how this, we think, the kind of feedback that the black hole has on the galaxy on larger scales actually determines whether it should be 3 or 4 or 5. Okay, so let me then quickly move on to showing you that we have abundant evidence for the existence of growing feasting black holes. So feasting black holes, I know this looks very unimpressive, and I did it on purpose. This is one of the most distant black holes in the universe. So this we are seeing, this is an image when the universe was about 2 gigayears old. Remember, today the age is about 14 billion years. So this is when the universe was 2 billion years old. And so we have a quasar here, which appears quite dim, but it's extremely bright. It's one of the brightest objects in the universe. The reason you don't see it is actually faint because it's far away, right? And we know it's there. We know from its spectrum where it is exactly in 3 dimensions. We know where it is. And we find that for the kind of brightness that it does have, so you can calculate the brightness that is unmitigated by the distance, right, which isn't dimmed by the fact that we're so far away, and you find that it has to be powered by those equations that I just showed you in the beginning. It needs to have a black hole that is 1 billion times the mass of the sun. Okay, just get this, right? So you have to have a black hole that is 1 billion times the mass of the sun. It has to be in place and feeding by the time the universe is only 2 billion years old. Okay, that's a challenge. It turns out it is a real challenge. And so these are other examples. So this is a duo of black holes. This is an X-ray image. So these are 2 black holes that are sort of dancing around each other. They're going to actually merge. And we'll see a little bit about them before I finish. And this is an image in the radio of another duo. So we see black holes basically everywhere. And I just want to show you, we see them in many different wavelengths. You see them in the X-ray, you see them in the radio, you see them optically. So these are, again, very bright quasars. And these are feasting black holes, as I said. So what you're seeing here is the accretion luminosity from that quasar that is gobbling gas. And this quasar is actually here, and we've subtracted out, because it outshines the entire galaxy. So this image, this is the galaxy that is hosting this black hole. Okay? So this is to just show you that, we see them all over the place. So just to give you a sense, so this is again one of those bright quasars. This is a Hubble Space Telescope image, and we think it's powered by a 10 to the 8 or 10 to the 9 times mass of the sun hole. So a billion times the mass of the sun. This is our galactic center. This is an image in the infrared. And what you see here is actually a star called Sagittarius A star. And remember, this is that the center of those orbits that I showed you earlier. This is just an image in the infrared. And we think that the mass of this black hole is about, as I said, 1 million solar masses. So what you find is there is almost no accretion going on here. This is not a popping bright thing. If this were a popping bright thing, we would see it, right? We're nearby, we would see it. In fact, we'd be fried if this was popping bright, but it's not. So this is an example of a fasting black hole, or, people initially thought they were dead black holes. Like, basically, you're dead, you're not. But the thing is, it turns out that you can't really tell the difference between a completely dead black hole that is not feeding at all to one that is really being force-fed at a tiny, tiny, tiny amount. Okay? So, that's why I like to call them as sort of fasting black holes. Okay, so then what is the evidence? I just want to go through this evidence very quickly so that I can then show you where the theoretical progress has been made. So this is again data, and this is to show you this argument about how far out do black holes affect their environment. So basically, it's like an atom bomb. I guess you have a bomb going off in the center of a galaxy when it's feeding. Huge amounts of energy. And it turns out that typically these black holes drive jets, huge, powerful jets out. And you might have noticed that in the animation that I showed you, right? That there's a little sort of jet coming out. So it turns out that there was a black hole here that spewed out a lot of material in the jets, and what you see are these shells, these echoes of that activity, and that is seen in the X-ray data. So what you see here are these holes and these cavities where the black hole jet has blown out gas and it's deposited some shells. Okay, so you see that. So you see that black holes actually have, and this scale is sort of outside a galaxy, very large cosmological scale. This physical scale from the center to here. So you see that they have a huge, okay, so let me quickly show you this calculation that will tell you why we are even thinking about new ways of making the first black hole. So that is one of the key areas of research, and that is one in which sort of I have a horse in that game. Okay. So if you started off with the initial mass of a star, so you made a first star somehow. Let's not worry about how you made it. We know how to make them. So you make the first star. It burns out all its hydrogen and leaves a little black hole at the end. Say that's 10 times the mass of the sun. And then I told you that when the universe is 2 billion years old, we already see a quasar, and that has to be a billion times the mass of the sun. And so you have 200 million, 2 gigayears, 2 million years, and you need to grow it up by 8 orders of magnitude in mass. The question is, can you do it? Just enough time. Okay, just enough time. So it turns out that if you had found only one of these guys, you can say, oh, okay, it's chance. This one just happened to be sitting in a nice gas-rich place, and you made them. It turns out, luckily for people like me, that you're finding populations of them. So you have to have a natural way to make them. You can't expect happenstance to have made one sort of obese black hole. You need to have an explanation, right? So it turns out, in addition to that, people who do, these are simulations of the formation of the first star, and people who do that, so you form a bunch of stars, first stars. This is gas. This is the density of gas. Tells you how packed the gas is, how tightly packed the gas is. So the red is very, very dense. So these little black dots are sort of proxies for the black holes that would be left from the first stars, the bunch of first stars that formed. And what you find is that, bulk of the gas is sitting here. Most of them start to drift away from the gas supply. So it turns out even if you make a whole bunch of stars, they leave black holes. If you follow them in a computer simulation, you find that these black holes, they kick against each other, they push themselves out. They actually end up in parts where there's not much gas. Remember, gas is what you need to feed. So they are not in an optimal feeding situation. So these guys, it's extremely difficult to get these guys to grow 8 orders of magnitude in 2 gigayears. 2 billion years. So you need other ways to make black holes. And so this is where me and some of my former students and postdocs have done quite a bit of work over the past 4 or 5 years. We started off with very simple models, and now they've become more and more sophisticated as we can actually simulate and do computer calculations. So this was the earlier wisdom. So population 3 is just a fancy way of saying first star. Okay, so first star forms, maybe you can make them very massive. Maybe the first stars we believe were extremely massive, say 10 times the mass of the sun or 100 times the mass of the sun. And then they actually leave you a black hole, which is 50 times the mass of the sun, say. But as we just found out, you can't actually grow them easily to explain the quasars that you see, the population of quasars that you see. So what do you need to do? Very simple solution. You need to make much more massive seeds to start out with, because then the challenge is an easier challenge. You don't have to grow them that much, right? So then there are a bunch of different ways. It's called direct collapse. So there are ways of coagulating the gas very, very early in the universe and making it really, really dense and forming a black hole directly without forming a star, bypassing the formation of a star. Okay? And we sort of think that we have some ideas about how we may be able to. It's not fully sorted out. This is sort of the frontier where all the debates are right now. Which of these? But the point is you can make these seeds much more massive. And that alleviates the problem of explaining how these extremely massive black holes came to be. So I just want to show you a cartoon. So this was a new idea a couple of years ago, and one of my postdocs, Dissemination, had, which is basically in the early universe, this is a dark matter halo. You have a lot of gas. This is before any stars have formed, right? So you have gas that has settled into a nice fat disk, and it gets unstable, and you start moving mass. It starts shoveling mass to the center, and then you form a nice little black hole seed, and then you form the stars around it. Okay, so this was sort of the picture, the naive picture. And then, we had a tough time convincing people. It was a simple picture. It kind of worked, and it was cute. But, obviously you have to show that this is plausible in the early universe. So this is just a slice from a simulation, again, of gas flows. So, everything is about gas flows, whether you can actually make those kinds of structures, right? Can you make a little disk? Can you make a nice fat blob of gas in the center? That could be the seed. It turns out that as far as we can go in the code, we can't go all the way down. Remember, this is the challenge of scales, because you have to get the gas all the way from large scales down to the very, very centers of what will be the putative galaxies in the future. What you find is that, yes, indeed, you can get these condensations, but we don't quite know for sure. This is sort of the edge. So these are the newest simulations. This simulation took 6 months on a supercomputer to run. Okay. So what this is showing you, again, this is density of the gas, and it's showing you that you can actually aggregate stuff, a pretty big clump in the center. That's all you really we wanted to see, right? How dense a clump can you get in the center that can make a seed? So these are from 2 different angles of the same clump. Okay, so this challenge, as I said, so this challenge of scales is to start from large-scale flows, gas flows in the universe, and get it all the way down to black hole. So these are simulations from Lucio Meyer and his group. And so what this is, so this is the size. This is a very large piece of the universe. So this would be a galaxy size. So look, we are about 1,000 to 5,000 times the size of an individual galaxy. That's the size of this volume of the universe that is being simulated here. So notice what you see here in red, these sort of filaments, they're actually gas flows. So essentially, this is the scaling problem, right? So there are gas flows in the universe. You need to get them down here. You need to form this galaxy. You need to get them right into that dot. So I want you to pay some attention to this green ring here. The reason is that I'm going to next show you a little movie where you see these 2 galaxies, M3 and M4, that are actually, so we're going to zoom in. We're going to lose this part. We're going to zoom into this part of the picture.
Can I ask a question?
Sure, please.
Like the previous picture with the network
Yeah.
that you showed, what is the dark matter doing?
Actually, the gas is following the dark matter. So the dark matter is what is causing the filamentary structure.
So if I were to plot the dark matter there, I'd also see a filament.
It would be following. The gas would be exactly following the dark matter. Completely mirroring. In a way, you can think of the dark matter as being the tube in which the gas is basically flowing. It's really guiding where. Yep. You mean from the when it's feeding? Yeah.
What role does that have? Any role in the spin of the...
Yes. So yeah, that is again, it's a much debated question, Sarah. Good question of whether when two galaxies merge or when gas is fed on depends on the orbit on which the gas is coming, whether it's prograde or it's retrograde, right? Whether it'll spin up or it'll spin down. Yes. So we have some sort of rudimentary understanding of how that goes and whether spins flip for the black hole, etc. So what I was just showing you here is a movie of the scale of M3, M4. So it turns out the way structure grows in the universe, things kind of coagulate, they merge, and you form the smallest galaxies early on, the smallest gas condensations, the smallest stellar condensations. They merge, they collide, they make bigger things. They coagulate, they aggregate, make bigger things. So they merge. So these kinds of violent collisions are very, very common in the early universe. I want you to pay a little bit of attention to this. This is million years, so 160 million years. I want you to notice this because I will show you when we zoom further in, the clock. That will give you the challenge of scales. You'll see that you have to be able to resolve, if you will, a process that is happening on a year's length time scale as well as a second in the same computation. And that's a huge challenge. That's sort of one of, yeah?
What determines the spin? Are they uniform spins?
They're not uniform spin. What determines the spins, as you can see, we believe the theory is that because gas flows in filaments into galaxies, and they torque and they pull each other. So the environment is what determines the angular momentum or the spin of galaxies, we believe. And we believe that actually it's and the merger history of how often they've merged and things have gotten rattled around. So you'll see that this is a merger of two gas-rich galaxies that are spinning and that are actually moving. So you're seeing them head on. They both have a feeding black hole. Okay, so this gas, so this is just gas that you're seeing. So the gas is actually being funneled at the moment. So they both have a black hole in them. Yes, indeed, in the early universe, you could have a few galaxies that didn't have a black hole. They would eventually get one because they will merge with things that had one. Merging is so common that you will get given a black hole even if you aren't born with one. Okay?
So,
yeah.
Theoretically, anyway, at some point, a black hole could reverse spin as a result of...
Yes, absolutely. The thing is that time scales for those events are, it would be cool to watch something like, but time scales, alas.
I don't expect to do that.
Yeah, neither do I. So what you're seeing here is how violent a merger is and how much of the gas is all disrupted. You have all these very complex flows. And what you're seeing here in red, it gives you a temperature of the gas. So some of the gas gets heated. Okay? It's heated from the tidal energy of the encounter and also heating from the feedback from these black holes that, as I told you, were feeding already. So in the end, you blow out a lot of gas and you have a major feast. A major feast for the one black hole. So you merge the black holes as well. That's right. And you end up with one single black hole. And so I just wanted to showcase another simulation from one of my former students, Pedro Capello. And what is nice about this rendition of the same, it's a different encounter, so different angles, different inclinations. And what you see here is that he's done this animation so beautifully that every time the black hole is feeding, you see the center flickering. See? You can see the flicker. So they're both feeding. And it's a slightly different angle. So what this shows you is that you can have a couple of passages. You may not just go thwack because that depends on how you approach. So this is sort of a more slow, gentle approach. And but nevertheless, it is pretty violent in the end. So the point about this is that we believe that the feasts, right, the feasting episodes, come from merger-triggered accretion because gas gets funneled in like a piston once you have these very violent merger. So you merge the black holes, there's all this gas going in, and that's when we think we have a bright quasar. Okay? So we think we've cracked when So it turns out all these different objects you see in the universe that are X-ray bright, that are in the optically bright, we think they're different stages of the phenomenon. So the feasting stage is quasars. And we know for sure that you feast whenever you have gas. One of the most efficient ways, the hose that feeds you, is triggered by the merger of two galaxies. It turns out that you don't have, not every quasar needs to be like this, only the brightest guys, okay? It turns out that's sufficient. So now this is another simulation from Lucio Meyer's group. Notice here, 0.05 million years. So the time scale on which action happens, this is closer in. We've gone into the nucleus. Okay, things happen much faster. So now we are looking at we are zooming in to the previous merger. And notice we are getting to see more of the details. So basically, this is the challenge, to see the details. And so what's the final? So the holy grail is that we want to resolve the kind of stage where we can see the gas feeding. We don't quite do that, right? We're nowhere, we're not quite near there, but we're getting close. And so just to give you an idea of where the future of the field is. So, you may ask, okay, this is great, but, what if I change the properties of the gas in the universe? Make it a little colder, a little hotter, different. It's called the equation of state. Suppose I make the relationship between pressure and density. Suppose I change that a little bit. How does it affect all of this, right? So that's what people are starting to do now. So that's the level we're at. We can actually investigate, okay, if the gas had a different equation of state, what does, and notice here that depending the kinds of structures that you get in the inner regions of a galactic nucleus do depend on the properties of the gas. But what still holds true is that you do funnel a lot of gas to the center. Okay, you still manage, the feast is uninterrupted. The question is, how big is your hose? How much stuff are you pummeling in? That depends on, so before I wrap up, I'm reaching the final couple of,
What is the youngest quasar that was observed, and what is the range of species?
Excellent question. So the youngest would be the most distant quasar from us. So the most distant quasar that has been discovered is at a redshift. The redshift is a way in which astronomers and cosmologists measure time and distance simultaneously, conveniently. And this is when the universe was less than 1 gigayear old, less than 1 billion years old. That's the record holder at the moment. But and who knows? It just may be, as I'll show you in 2 slides, that perhaps the first black holes that fired up and made the first quasars were likely in very dusty places because stars were just starting to form afterwards. And so they may be very dust enshrouded. So we may not be seeing them till we see in the infrared. And that's going to happen in a few years with the James Webb Space Telescope. It's going to uncover, hopefully, a lot of these dust-enshrouded quasars. So the question is, you may say, oh, this is all great. Your merger movies are great, but does it happen in the real universe? Yes, it does. So we see a lot of mergers. So and the question of what happens, someone asked me this question. So this is a movie from early work that I did, one of my collaborators, Philip Armitage. What you're seeing is a head-on view of a galaxy nucleus. A very massive black hole is sitting here. During the merger, the second guy, the black hole that was sitting in the second galaxy, has plopped onto it. And it starts migrating to the center. So this is the gas disk, and it starts spiraling in, and it's going to eventually make it all the way in. And notice one of the curious things about this is that this disk, the gas disk, this is the inner part of the disk, the second guy plowing through makes a big gap, kind of opens up this gap. And that's what you're seeing here in case you're curious. You kind of cut a gap. If you remember when you first started out, the entire disk looked like this. It was sort of an exponential. And then with time, as the second guy is grinding in, you're actually moving gas out. You're piling it out in the outskirts, and you're piling some in, and you are creating this gap. So this is, this allows you to then put everything together, and this is the picture that we currently have. That you have merging galaxies, you make the brightest quasars. This is the story for the brightest. This is for the giants, the behemoths, right? And they are kind of obscured for a little time when they're copiously feeding during the merger. And then all the dust clears, and you see what is an unobscured quasar, this bright beacon of light. And we now have a reasonably good idea. So we are clocking it now. So we know once you make, of course, you need to have made the holes already. That's a different part of the problem, right? We've made the holes already, the first holes. And now we think that after every feeding episode, these feeding episodes are pretty long, and that you are obscured for about 100 million years, then you're unobscured for 100 million years. And we think that every time two galaxies merge, you can kickstart this process. You can have a feast. And you can become extremely obese by having feast after feast. Okay, so I want to wrap up now and to talk very briefly about this new window that I sort of tantalized you about when I said there's this whole new window that needs to be opened. Okay, so it turns out when two black holes merge, the dying gasp of two merging black holes produces gravitational waves. Okay, so it's energy. Basically, it is like energy that is produced by shaking space-time. Okay, these two black holes. Remember, now let's go back to our puncture picture, right, of black holes being these punctures. So they are merging, and finally, when they merge, they release gravitational radiation, i.e., some of the energy that was in the orbit, right, gets transported to space-time. So space-time gets jiggled when they actually finally merge. And it's a jiggle that we can measure. We haven't done it quite yet, but, and one of the reasons, so one of the exciting things in the past 7 years or so has been being able to do these simulations of the kind of jiggle that would be produced, the signal. What does the signal look like? So theoretically, people had predicted what these signals should look like, but the question is, we want to know from a simulation. Remember, the whole goal of these simulations is you want to span all the scales. So this is the final frontier. So very recently, there was a breakthrough that was made, and it was made by two independent groups. This was a problem that people hadn't solved for decades. They didn't know how to do it, how to get two black holes to merge, as in how to solve the problem in general relativity. With the metric, with all the space-time curving and all that, they couldn't do it, right? Computationally, it was intractable. Till there was brilliant insight by two different groups, roughly at the same time. And they've now cracked the problem, and they can actually predict. So I'm just giving you the theory, theoretically what should happen, what the signal should look like, what we need to look for. And so what is this when two black holes they are in the stage of inspiraling, so they're still a little far apart, and you start having gravitational waves being emitted already because the orbit, the angular momentum of that orbit, you're grinding down, so you're losing angular momentum. You are losing orbital energy, and that starts to get dissipated in gravitational waves. That's sort of these little red arrows. And this is the kind of signal you should get. And then there's the stage when they actually merge, and you should get this kind of signal. And now, finally, computer simulations. So we knew what should happen here. We were able to predict what should happen here. Computer simulations have allowed us to bridge this key gap. Because we need to look for the entire signal, because you never know what stage you'll be catching a merging binary in, anywhere in the universe. So this is my final slide, which is basically these are gravitational waves. And for those of you who are engineers, notice the frequency. We're really talking about, millihertz for coalescing black holes in the universe from cosmological distances. So this would be from everywhere. Things are happening everywhere. We'd sort of have this collective signal, and it could be detected. So what is shown here in red was a proposed instrument that would have this kind of if it had a sensitivity curve that looks like this, it would be able to detect everything above that. So it would actually catch all the merging black holes. Alas, this project has run into a bit of funding trouble, and hopefully it'll happen eventually. But then these are gravitational waves that so these would be supermassive black holes. So neutron star and lower mass black hole coalescence will have a different signature in a different frequency space. So we understand that very, very well. So this is sort of the final window, because this is really the innermost, a test of the gravitational physics, test of gravitation, a test of relativity, of general relativity, down to the smallest scales. And in a way, it's also really a test of whether we have, even at some level, managed to bridge all the scales in this problem. So anyway, I will stop here, and thank you very much for your attention. I think Jörg had a question.
So many questions were asked, and I bet there's a lot more left. So Kevin's going to help me. So hold your question till I can get the microphone to you, okay? So let me start here in the front row.
If you have a non-rotating black hole and a particle, let's call it a spaceship, that's falling from infinity, does it reach the speed of light at the event horizon?
Yes.
Now,
asymptotically.
Now, that leads to, I just wanted to be sure of that because
Okay.
I thought it.
Notice I hedged my bets very nicely by telling you asymptotically, but yes, yeah.
So you have an astronaut here. Now, as you get closer, you speed up, and as you approach the speed of light, the thickness of the spaceship and the direction it's going thins down.
Thinner and thinner, yes.
And time drops
Dilates.
to zero.
Yep.
Okay. My question, does the astronaut ever get into the black hole? And
Not from that spaceship. Not from this.
how can black holes grow?
Oh, a black hole. What do you mean? Black holes grow because. So your question is, how is a packet of gas? We don't know what happens when it passes the event horizon. So what we really calculate is when something gets to what is called the last stable circular orbit. It is 6 times the gravitational radius. And basically at that point, we know it's gone beyond, it can't turn back. It's going to go in there. So as far as we know, we need to get the gas down to 6 times the gravitational radius. And then, the extreme gravity of the black hole does its job for us. And we actually don't know what is the state of matter, what are the thermodynamics of it. No idea. We just need to get it there.
And it's gone out of the universe.
Yep. Out of the universe. Yep.
We have a question back here.
I read in a book, and I want to know whether you agree with the statement. It said the speed of light in a black hole is the same as the speed of light outside black hole. And in order for it to keep that speed, the photon has to give up energy. And when it's given up all its energy, it ceases to be a photon.
Yeah.
Now, the other thing is, of course, the wave that comes with all the particles, that in a black hole, the wave is straightened out, and when it's straightened out, it becomes flat.
Yep.
So it's all gone.
Right. So, he's asking these very important, interesting questions, which are very, very difficult. I'll tell you why they're difficult, right? So once you start getting in pretty close to the black hole, you need to understand the interplay of strong gravity and quantum mechanics, which we don't quite yet. So, so all I can tell you is that I really don't know anything about the inside of a black hole. And I think every physicist will tell you that basically, they're speculations, but they will basically tell you, I know the outer boundary, I know the Schwarzschild radius, that's about it. I don't know anything. And the speculation is as you approach. So, if you were an astronaut, if you had been dropped from infinity into the black hole, how would you fall? So it turns out, this comes back to this firewall paradox question. So basically you would be stretched out, right? So you would be stretched out along one dimension, you would be really stretched out. You would become like a little spaghetti string. However, your temperature would also go up, so you would really be nothing by the time so so these are very tricky questions because this is the interplay of strong gravity where classical physics doesn't work. So, you have to have understanding of quantum mechanics and how that actually interplays with strong gravity, with strong gravitational fields. We don't quite have a theory. Yeah.
There was something really basic I missed at the beginning. You said that the doubling time is like 40 million years
Yeah.
for all black holes.
Yeah.
But I don't understand. That's by accretion?
Yeah, by accretion.
So that must depend on the environment, doesn't it? Or?
Yeah, it depends on gas supply. So if you have the gas, that's what you'll do.
I see. So it's not always 40 million then?
No, in the sense that if you, for example, the galaxy, the black hole, at the center of our galaxy ain't doubling. It's not doing anything because there's no gas that's feeding
that's
it.
just the limit of how fast it could be if there's enough gas.
If there's a gas around.
Oh, I see.
Yeah.
Okay.
Question back here.
Does the behavior and consistency of dark matter have anything to do with this?
Excellent question. So it turns out that when I showed you all these, so right at the center, so right at the center of a galaxy where the black hole dominates the gravitational potential well and it has a little region of influence, there's not a whole lot of dark matter. So it's baryons, ordinary atoms, gas that dominates. But as you go progressively outside a galaxy, it turns out that dark matter starts to dominate, right? So, for example, when two galaxies merge, because the entire galaxy is at play, the dark matter halo, how extended it is, how much there is, makes a huge difference to how things will actually flow, what generates the flow. So, I guess the scales, right? The scales on which dark matter is important is not pertinent to the feeding problem, but it's pertinent to the feedback, the effect problem. So if you have a jet, how far out a jet can punch out depends on how much dark matter there is. So for example, right, just a quick, I feel like I have to write something on the board because it's supposed to be a chalk talk, right? So if this was the distance from the sun in the solar system, right, and if you look at the speeds of the planets, looks like this, right? So Mercury, Venus, us, Pluto, I still think is a planet, is moving very, right? So, right? But if you play the same exercise in a galaxy, what you find is this. Okay, so as you go farther and farther out from a galaxy, the speeds of stars does not fall down. What that's telling you is the gravitationally, so what does this tell you? This tells you that the gravitationally dominant object in this game is sitting at the center, the sun. Okay? This tells you that the gravitationally dominant object is everywhere here. It's distributed in an extended envelope. Okay? So that's why dark matter doesn't play an important role, which is where the black hole is sitting in a galaxy. There's not very much dark matter here. As you go out, there's a lot of dark matter. So when we are looking at the gas feeding right onto the black hole, the dark matter is not very relevant. But where it's relevant is how gas comes in from the large scales all the way to the center. And how when galaxies collide, and that web that I showed you, those filaments, right? And I told you the dark matter is actually the tube. So it's really important. So where the dark matter is going to direct is where the gas is going to flow. The gravity of the dark matter.
You spoke about gravitational or temporal waves being given off during the merger of the two black holes. Does this have anything to do with the fact that you have two event horizons at which time there is no time existing or time movement? Those then come together and they have to, I assume they deal with time by the fact that it's gradual. It goes from no motion of time at the event horizon all the way out to the top of the black hole where there is some to where there's a flow.
So you see, when the black holes are actually merging, right, by that time, they are so close in that there's no gas or anything. It's all, it's a really, really small scale. So you really are looking at the sort of the two punctures in space-time. So it's the energy that's coming out. Indeed, it's true that when the two event horizons meet and merge, as it were, the notion of time changes. But what is really happening, I think the easier way to think about it is to think that when these two sort of punctures in space-time get together, they kind of merge, and the two event horizons merge, you kind of release this energy that jiggles space-time. So they sort of can think of it as sort of a jitter in space-time that's produced, and those are those waves.
So it's more of an explosion versus a stopping of time.
wouldn't call what we are measuring. We're measuring actually energy. So we're not really measuring a change in time, in the nature of time or anything like that.
But the event horizon is, in effect, absorbed all energy, and jiggling in time almost seems to be an expulsion of energy.
Right. So jiggling in space-time is coming because you are you have a non-zero quadrupole moment. So you're breaking sort of symmetry, and that's what's giving you that jiggling.
Right.
Yeah.
Question over here.
Is the only factor governing the time between feasting and fasting the amount of available gas, or are there other factors?
And the spoon, like what's actually whether you can actually get the gas down. So there are instances where we see galaxies where there appears to be gas, but somehow it's either too hot or it doesn't actually make it down. So you don't see a quasar, but you see some hot gas sort of sitting around. So it is gas supply and also physical mechanisms that will actually drive the gas in. And so we have a whole set of mechanisms. Other than these sort of mergers, we think that you can form these bars in galaxies that rotate really rapidly. So, okay, what is the problem here for the gas? So the gas has spin. It has to get rid of its angular momentum. It has to get rid of its angular momentum, its spin, before it can actually make it to the center. Because, it'll miss the center. It'll be moving around. So you have to grind down to get to smaller and smaller orbits, i.e. lose angular momentum or spin, so that you can go thwack on the black hole, right? So we have other ways in which you could lose the angular momentum. And one of those ways is called a bar. So basically, it's a bar that removes angular momentum from the gas very rapidly and makes it sort of spiral in. And these bars can be either stars or gas bars.
I see two more questions. After that, I think we have to wrap it up.
You said when material accretes into a black hole, it accumulates the gas radiates.
Yep.
Is that radiation from gas molecule collisions and de-excitation, or is it conventional classical radiation from accelerated charged particles?
It's a classical radiation because it's just a small portion of the rest mass energy of the gas as it's going in.
So the gas is not dense enough to have significant numbers of collisions?
No, it is. It is. So it's Bremsstrahlung.
It's Bremsstrahlung.
So you would see it in X-rays, for example.
I've heard a lot of talk about dark matter, but does dark energy enter into this conversation at all?
Not in this game, except in setting the clock, right? I mean, the age of the universe has to do, so Einstein's big thing was the contents, the age, and the fate of the universe are locked, basically. And so if we didn't have dark energy, we would have a slightly different age for the universe. So we'd have a different timeline to play with. But per se, in terms of feeding the black hole itself, or sort of these scales, dark energy is not overall relevant. I mean, of course, it's overall relevant for sort of the shape of space, etc., but not, thankfully, don't have to deal with all exotica in the same game, right? So.
Okay, if you have further questions, you might catch Priya after the event. But let's all thank Priya for a great talk.
Thank you so much. Thank you.